So hello everyone, myself yes Sanjay Suryavanshi. This is a video related to the topic of computer graphics. The subject of this video is polygon clipping algorithms. Let's begin. So the overview of this video is that it contains some definitions. The first polygon clipping algorithm, some drawbacks, the second polygon clipping algorithm, and the conclusion. So let's start with some basic definitions. First is a polygon. So a polygon is a 2D geometric figure that is formed by connecting straight line segments. These line segments are called sides or edges, and the points where they meet are called the vertices. Edge and a vertex. Minimum 3 vertices and 3 edges are required for a structure or a shape to be called as a polygon. The next is clipping. Clipping refers to the process of determining which parts of a graphical object or scene should be displayed on the screen. The window against which object is clipped is called a clip window. In this case, this is the clip window. So let's start with the first polygon clipping algorithm, the Sutherland-Hodgman algorithm. It performs clipping of a polygon against each window edge in turn. The order to clip the polygon should be clipping against the left side of the clip window, clipping against the top side, the right side, and the bottom side. So consider this as a polygon, and this is the clip window. So first we'll perform it clipping against the left side of the clip window, then the top side, then the right side, then the bottom side. So it consists of 4 cases. Okay, consider this as the clip window, and this is an edge V1, V2. Now, if you are traveling from V1 to V2, there is an intersection point. So, if you are going from outside to inside, what we have to do is save the intersection point and the destination vertex in an output vertex list. I've just described this here. Okay, so we're going to save V1 dash and V2 if you're going from outside to inside. The second case is pretty simple. If the edge is completely inside the clip window, then we have to just save V2. Okay, if we're traveling from V1 to V2, just save V2. The third case is simple. It's from inside to outside. If we're going that way, V1 to V2, in this edge, we have to just save the intersection point of the edge with the clip window. And the fourth case is pretty simple. If the edge is completely outside the clip window, we are going to save nothing in the output vertex list. In order to better understand the algorithm, let's see a numerical. So the question we are asked is for a polygon and clipping window as shown in figure below. Give the list of vertices after each boundary clipping. This is the polygon. 4 vertices, clip window. Let's go. So first we'll perform left clipping. Consider the left side of the clip window. Another thing that we noted is the intersection points V-1, V-2, V-3, and V-4 of the polygon with respect to the clip window are mentioned. So let's start with V1 to V2. Okay. In that case, we have the intersection point. We are going from outside to inside. So the intersection point and the destination vertex will be saved. They are saved. V2 to V3 will be the proper choice, but V-2 is also lying. So we go from V2 to V-2. V-2 will be saved because these are inside with respect to the left side of the clip window. So we save the destination vertex. So V-2, V-2 to V3, V3, V3 to V-3, again V-3, V-3 to V4, V4 will be saved, and V4 to V1. Now, we are going from inside to outside. In that case, only the intersection point of the edge with the clip window will be saved, V-4. This is the output vertex list for left clipping. Now we can see that V1, this vertex has been completely eliminated. So let's start top clipping. We'll start from V-1. Just save it and start from V-1 to V2. Again, inside with respect to the top side of the clip window. So save V2 and V-1. Now, if you go from V2 to V3, inside to outside, in that case only V-2 will be saved, V-2. Now, if we go from V3 to V4, that is outside to inside, in that case the intersection point and the destination vertex will be saved, V-3, V4. And if we go from V4 to V-4, again inside with respect to the top side of the clip window, V-4 will be saved. This is the output vertex list. Now, if you pay close attention, we can see that the polygon is just intersecting with the left side and the top side of the clip window. It is virtually not interacting with the right side of the clip window at all. So the output vertex list will be very similar or is just same with the top clip. All of these are inside. So if you go V-1 to V2, only V2, start with V-1 will be saved, V2 will be saved, then v dash 2 will be saved, v dash 3 will be saved, 4, v dash 4 will also be saved. So what is the difference is that v3 has been completely eliminated. Same goes for bottom clip. It is just not interacting with the bottom side of the clip window. So just follow the same cases and that's it. We perform left, top, right, and bottom clip. This is the final clip polygon. And here we go. We perform the Sutherland-Hodgman algorithm properly. So the drawback with the Sutherland-Hodgman algorithm was that it correctly clips convex polygons, but concave polygons may be displayed with unnecessary lines. Okay, this is a concave polygon, and if we perform clipping with respect to Sutherland-Hodgman, this unnecessary line will be displayed. So in order to solve that, another algorithm was devised. So the second polygon clipping algorithm is called the Weiler-Atherton algorithm. This algorithm can perform the clipping of a concave, the main topic, and convex polygon as well. Perform a lot of clockwise processing in this algorithm. For that, for an outside to inside pair of vertices, we follow the polygon boundary. For an inside to outside pair of vertices, we follow the window boundary. This clockwise processing will make sense as we go ahead. Let's see the algorithm steps. First is that we assume the polygon is listed in clockwise order. If the edge enters the clip polygon means the clipping window, nothing else. Record the intersection points and continue to trace the subject polygon. Subject polygon basically means the polygon that we are provided with. If the edge leaves the clip polygon, record the intersection point and make a right. Follow the clip polygon in same manner. That is, treat clip polygon as subject polygon. This is a vast point. It will be clear as we go ahead. Continue until vertex reach visited vertex. Okay. 4 steps. Let's go. So this is our question. Let's understand the algorithm better with it. So subject polygon, as I said, just the normal polygon we are given, and clip polygon is nothing but the clipping window. Okay. So let's solve this numerically. So first step we're going to do is clockwise notation to the subject polygon. Okay, V1, V2, all the way till V6, back to V1 again. Intersection points with the clip window are noted I1 to I4. So next, what we do is we start from V1 to V2. Again, clockwise direction, both outside vertices. Just record them and go ahead. V2 to V3. Now, this is outside to inside pair again. An intersection point is also being there. So record this and V3, V2, I1, V3. Okay, let's go. Now, V3 to V4, again, clockwise direction, both inside. Okay, so just continue, record them and continue V3 to V4. So let's see step number 5. From V4 vertex to vertex V5 in clockwise direction. Okay, V4 to V5 in clockwise. Here, both V4 inside and V5 is outside. So continue to clip polygon clockwise to intersection point from I2 to I1. Also clip the polygon. Little tricky. Now, V4 to V5, we are going from inside to outside. As I stated in the very first slide, inside to outside pair of vertices will follow the boundary. Okay, window boundary. I2 to I1. So we don't go from V4 to V5, we go from V4, I2, and I1. Okay, that's what is mentioned here. In the next step, we start from V5 to V6. Again, the intersection point is there. So record I3, V6. Okay. In the next step again, we go from V6 to V1. Inside to outside pair of vertices. We follow window boundary. So V6, I4, and I3. Again, V6, I4, and I3. In the end, 3 vertices, V1, V2, and V5 are completely eliminated, and we get a clipped polygon. And we also don't get an extra side or edge, okay, which we would have obtained with the earlier Sutherland-Hodgman algorithm. This is the end of the Weiler-Atherton algorithm. So in this way, I've explained the two popular polygon clipping algorithms. They find a lot of use in computer graphics. The information derived is that the Weiler-Atherton removes the issues with Sutherland-Hodgman and is much more better. Thank you everyone for watching.